Good evening, everyone. I hope you all are having an enriching time in this AICTE sponsored ATAL Faculty Development Program. Each session has been an evidence to how technology is advancing and shaping the world around us. We are now moved to technical session 7, which is focuses on one of the most innovative and exciting intersection of science and technology, application of tissue engineering in 3D printing. This session will explore how 3D printing is enabling breakthrough in tissue engineering, bridging the gap between medical science and cutting-edge engineering to create solutions that could redefine healthcare practices. To take us through this fascinating topic, we have with us highly accomplished expert Dr. Ashutosh Bagde. We are honored to welcome Dr. Ashutosh Bagde, Additional Director of Bionest at Datta Meghe Institute of Higher Engineering and Research at Varda, Assistant Professor of Biomedical Engineering at DMIHER Varda. He is an accomplished researcher with a PhD in Mechanical Engineering from Vishweshwarya National Institute of Technology, Nagpur. Dr. Ashutosh specializes in 3D bioprinting, tissue engineering, and organ regeneration. His work has earned him 2 patents and over 30 peer-reviewed publications. He has successfully led multiple high-impact funding projects with BIRAC, ICMR, and Department of Science and Technology. Dr. Ashutosh's expertise in additive manufacturing and biomaterials continue to drive impactful research and innovation in healthcare. His innovation work bridges the world of engineering and medicine, addressing challenges in organ repair, regeneration, and drug testing. We are truly privileged to have Dr. Bagde here to share his insight on how tissue engineering and 3D printing are revolutionizing medical science and improving patient care. Let us welcome Dr. Bagde sir to enlighten us with his presentation. Sir, over to you.
Thank you very much, English. Just I am about to share my screen. So I think it is visible right now.
Yes. Only you have to make the slideshow.
Yeah.
Now it is okay. Yes.
Okay. Na? So thank you very
Correct.
much, Nilesh, for introducing me, and again I'm thankful to Abesa and Jadusa for giving me another chance to speak with the faculty members for this FDP. And today yesterday we just discussed about the application of 3D printing in biomedical domain. Today we are going to discuss more concisely about the application of 3D printing only in the tissue engineering. So these are some outline where I'm going to take you. I will try to address some of the future scope of this tissue engineering, and I'm also trying to address some of the challenges which we really face in the tissue engineering. So I am anyone from the participant or faculty member from this FDP would take it as a challenge, either in their PhD work or either in their research work. So I will address some of the challenges associated with the bioprinting also. So as we already know about the solid film fabrication process, what is the workflow for additive manufacturing? The first thing is we need to create the CAD model. Then once we are creating the CAD model, we need to convert it into the STL format. Yesterday we already discussed this, but I am just giving the brief of that. So you will be with me during this presentation, entire presentations. And then once we are converting that 3D model into the STL format, we need to give it to the system, which only understand the 2D slice data. So we need to slice the data. And once we are doing the slicing of the data, we need to give it to the fabrication machines or 3D printing machine, additive manufacturing machine, whatever it is, SLA, FDM, SLS, whatever it is. So we need to give it to the 3D printing machine. And once it is given, the 2D slice data is given to the 3D printing machine, we will give the final finished 3D part, which required always some kind of post-processing. The post-processing is associated with the material or with the manufacturing process which we are using. So the few types of 3D printing process that we already discussed are stereolithography. If you remember, this is the same photograph which we discussed last night. So in stereolithography, require a photocurable polymer, which will be get cured by using the laser, so UV lights. So once one layer is get cured, the build platform will lower down by one layer thickness, and another layer will get again solidified based on that. Then another one of the additive manufacturing process is the SLS, that is selective laser sintering. Now what we are doing in selective laser sintering, we are using the metal powder, a fine metal powder. We are putting in a bed. We are just sintering it with the high laser intensity. And once it will get sintered, the build platform will lower down by one layer thickness, and another layer of the fine powder will come on the surface of the build platform. So by this way, we will get the selective laser sintering. Then next is about the 3D printing, which is also called as the binder jet printing. In binder jet printing, what we are doing, we are spreading the binder in the desired form in which we want the final outcome. And the very common is the FDM. So in FDM, we are using the plastic filament, which is in a form of spool, which will come to the extrusion nozzle and get melted and heated and melted and come out of the nozzle and printed in a build platform. So this already process we discussed uh, last session also. And now when we are talking about the 3D printing application, so we already discussed nowadays every field has some kind of 3D printing application, starting from the food, aeronautics, then aerospace, dental, electronic, toy, and everything. There is now, I don't think that there is any kind of field where the 3D printer is not being utilized. And when we look at the evaluation, so 3D printing is a very old process which is evolved in 1998, and till 2032 it is getting evolved, and it is expected that we in 2032 and all we will have the full body organ printing or in situ bioprinting manufacturing. In 2013 to 18 we are evidence that we are getting the biomedical implant 3D printed, that is all called as metal 3D printed implants also. And from 2013 to 32, it is expected that we will get the in situ biomanufacturing, and by the end of 2032, in developed country, we will get the full body organ to be printed and regenerated. So before we go to this tissue engineering concept, it is important for us to understand what is the regenerations. So regeneration is a term which we can be understand from the nature itself. The photograph is self-explanatory, which will give the example of the best kind of regenerations. So once we cut the plant, it will get again regenerated. This phenomenon of regeneration is what we need to employ in case of the tissue engineering. So if someone will say it is okay with the plant, so if you take the another example of the nuvette, you will find it will get regenerated. If you take the example of nuvette, you will find within 6 to 9 weeks the complete hand or their tail will get regenerated. So in living woods or in living organisms, it has the natural tendency of the regenerations, and this is nuvette is a very good example of this. Now what is basically going to happen in the case of this nuvette limb regenerations. So initially, if we see the figure A, it is an intact body. If you see the figure B, it is a trauma caused. Then what is happen after the trauma? Initially, it won't get healed. Then blastoma formation. Now what is in the blastoma formation? The stem cell responsible for the regeneration come across to that wound heal part or trauma part, and then we will start the redifferentiation. So stem cells, which is the basic cells of our body, will differentiate into the cartilage first, which is shown in figure E in the yellow color. And then after it get converted into the cartilage, it finally converted into the skin and bone as shown in the figure F, the development phase. So this is basically a regeneration cycle for this nuvette, and this is also true with the humans also. So when we are talking about regeneration in human, so it is very surprising that our entire body is capable to get regenerating with the different scenarios. So if you see our hair, it will go 0.35 mm per day. The growing rate of hair is 0.35 mm per day. So what is going to happen with the hair? It is getting regenerated. We are cutting it and again it get regenerated. So if you take about the virtual cortex, so it stops once you are going regeneration after some time. Okay, so if you choose the different muscle, the skeleton, so it is expected that skeleton is replaced after every 10 years of the skin of our life. The skin cell will get replaced in 39 days. Toenails got growing rate of 1 mm per month. It get regenerated. So if you see this figure, you will find what is the time duration required for regeneration of this body organ. So pancreatic beta cells get stop regeneration after the 30 years, but till 30 years it get regenerated. If there is an injury till 30 years, it will get regenerated. After that, it will stop. Heart muscle stop growing at the age of 10, but till 10 years it has its own regeneration capacity, and once it gets fully regenerated, then it stop its regenerations. So 98% of the body get rebuilt in less than 365 days. It is said that, and regeneration capacity always of humans is always decrease with the age. So as the age goes on increasing, the regeneration capacity is going to be decreased. Now, the which factor affect basically the regenerations? No doubt, age is one of the factor. Sorry. No doubt the age is one of the factor, but the another factor is loss of organ or tissue. So if there is some trauma cases and we suddenly lost some kind of organ, then definitely it affect the regeneration, and too much damage of the damage of tissues, like skin get burned. Skin has the natural tendency of regeneration in 39 days, but if skin get burned, it is very difficult to get regenerated. Blood, the leukemia or extreme blood loss, if there is some trauma and extreme blood get lost, it is then regeneration is very difficult. Or you are affected, or some patient is affected with the leukemia, that is the bone blood cancer, then regeneration get affected. Now in case of the bone, if there is some tumor removal or crushing injuries happen to the bone, then the regeneration capacity of bone also get replaced, get hampered. Now, in such conditions, when we are saying that if there is this factor which affect the regeneration, so what is the solution for that? The only solution for them with that conditions is the natural and artificial tissue replacement. So before we understand this natural and artificial tissue replacement, I would like to show some statistics. So in USA, the patient waiting for the organ replacements is explained here. So as per September 2024 data, there are 89,000 plus people who are waiting for the kidney replacement. 9,000 plus people are there who are waiting for the liver. Pancreas is 850. Kidney and pancreas replacement, there are the 2,000 plus patients who are waiting for this kind of replacement. 3,000 plus people are there for heart replacement, and there are so long. So this is basically a data for USA. Can you imagine the data for the India? USA is very good in maintaining the health record data, and also this is the condition with the September, just 2 months back. And can you imagine the what is the requirement of organs in India? So in USA, it is said that 90% of the US adult support the organ donations, but only the 60% are actually signed up as a donor. So if you are talking about the organ donations and all, government of India and any government is putting any kind of too much efforts to make people aware about the organ donations. In US, 90% people are agreed to donate their organs after the date, but only 60% are actually signed up as a donation. What it means, although they are dying, what is their death condition and all, out of that, only 60% people are eligible to get the organ to be donated. Uh, this waiting list is as per the September 2024 data, but in every 9 minutes, another person is added to transplant waiting list. So this is a statistic which we are taking from some US website, donor website, which I will just show here. And only 3 in 1,000 people are getting died, which allow the organ donation. So if we are considering 1,000 people dying in a month or in a day, out of that only 3 people are dying in such a way that they can be eligible to donate the organs. Now, on the similar line of action, you will see the data for India. There are 1,80,000 people who suffered from the kidney failure, and actually per year the kidney transplantation done in India is 6,000. The huge gap between this transplantation. 1,80,000 people required the kidney, but actually the transplantation done is 6,000. Forget about the cost associated with this. It is about the unavailability. It is not about the cost, that it is kidney transplantation cost is very high. It will be cut done only performed only in metro cities, and forget that part. Just look at the figure and differentiations, and as a technical person, how we can assist them. We are not supposed to do a surgery, but how we can produce a technological solution, that is the main of questions. There are 30,000 plus Indians who require the liver transplantation per year, while 1,500 liver transplantation are done only in India. 50,000 plus heart failure are reported in every year in India, and 15 only 15 plus heart transplantation is done every year in India. And same case with the cornea and cornea transplantation. So this is the Indian data per year. Unfortunately, as like USA, they have the organ donor, the site which is mentioned in footer. We are not having such kind of dedicated site now. Now the government has taken the initiative to prepare the database, but still we are not. We are very far away behind that. So the data which I got is basically for the per year requirement. So it might be possible the per year requirement is much more than that. Okay. So just think out as a technocrat, as a technical person, whatever the field you are, how we can help with this. Because if there is any person in your surrounding suffered with the kidney failure, then you can understand the pain associated with them. So this is the basically requirement for understanding why we require to work on the tissue engineering. So according to International Osteoporosis Foundation, 6.3 million fracture occurred every year in US. One of the three women and 1 out of 5 men are subjected to bone disease. And by 2050, with the incidence rate, it is projected that it will increase by 350% in men's and 240% women in 1990. So data which is available for 1990, it is expected that 2050, it is much more higher than 350% higher and 240% higher in men and women respectively. So this data has some authentic values which you can see over here. So out of this 50% fracture are expected in India, and due to and the basic reason is due to the low bone density. So if you have your grandparents or your mother and father, they often used to complain that they are having pain in their legs. It was the joint is getting pain. Why it is? Because we have the lower bone density, and it is with the heredity part of the Indian populations. It is in our genes itself. So that's why when we are expecting that 350% higher rate in 2050 worldwide, out of that 50% fracture are expected in India. So I'm just talking for the bone. Initial slide, I give the complete picture of the entire organ to be replacement, but I'm most now coming towards only the bone because my research is mostly aligned with the bone regenerations. Now, what is the treatment modality of the fracture? So if fortunately, unfortunately, anyone from us or everyone from us had some kind of accident while playing, riding a bicycle or playing something. And what we come to across such kind of things that when there is a fracture, the doctors are putting a metallic screw, metallic rod, or metallic wire. Now, what is the disadvantages associated with this? The disadvantages associated are stress shielding, which means the load acting on that part is completely taken care by the completely taken by the metallic part, and that which cause the stress shredding, and the associated part with that implant get osteoporosis, metallosis, and some kind of allergies. These are the basically the disadvantages associated when we are putting with the metallic implant. So what will be the solution? Now the putting the metallic implant is called as the reconstruction. Now the trend is moving from the reconstruction to the regeneration rather than reconstructing with the metallic implant. Is it possible to reconstruct the organ itself? And that's why this field of tissue engineering come into existence. So as explaining this figure, if there is some kind of bone defect, we are putting the 3D printed scaffold along with the cell and some kind of signaling molecules. We are implanting it to the side which cause the osteoconductor or osteointegration, and after the sometime we are getting the healthy bone. This is a very layman cycle of tissue engineering. So the solution for converting reconstruction to the regeneration is about using the tissue engineering. Now, when tissue engineering basically start? So tissue engineering term is basically coined in 1988 in National Science Foundation workshop. And these two people are basically the founder of tissue engineering in the world. They are the Langer and Vacanti from MIT, Massachusetts Institute of Technology, who basically give the definition of tissue engineering. And their paper in 1993, in which they have grown the ear in the rat back sides, is very famous that time. And they are called as the father of tissue engineering worldwide. So they define the tissue engineering as a multidisciplinary scientific branch that combines the cell biology, regenerative medicines, material science, and the engineering. So if you see, I always used to say to many people who they visit to our lab, I am a core mechanical engineer. I did my diploma. I haven't did 11th and 12th. I does not have any kind of biological support or understanding before I entered into the field of tissue engineering. So the person like me who does not understand biology at all, if he can work in the tissue engineering, so people like who did 11th, 12th and who are more fascinated about the biology, definitely they can work on the tissue engineering much better way than me. So if, as the definition itself say, it consists of cell biology, regenerative medicine, material science, and engineering. So it is completely a interdisciplinary team or multidisciplinary team, and it always welcome the any kind of people from any background, if they are from physics, chemistry, basic sciences, life sciences, engineering, even computer science also. So tissue engineering is a field which can include any kind of engineering prospects. So what is the clinical applications of tissue engineering? Now you just name the disease or you just name uh, the department, you will find the application of tissue engineering. In cardiovascular, yes, there is a application of tissue engineering, cardiomyocyte interactions and all. Recently, we received a fund from the ICMR for almost 1.5 CR for cardiovascular regenerations, and we are now venturing into the cardiovascular regenerations. In cancer associated with neurology, gynecology, orthopedic, or any kind of thing, yes, there is application of tissue engineering and cell culture, cell therapy. Dental, yes, it has application. So you just name the department, you will find out in this diagram how tissue engineering can be helpful and how tissue engineering can be integrated with this. So we are not going to worry about, or we are not going to discuss about the every part of this application of tissue engineering. We are just concentrating towards the orthopedic implant. So in orthopedic, it consists of bone grafting, vertebral disc damage, ligament damage, cartilage damage and repair, and non-union fractures. So these are the area where we are going to talk about in our next upcoming slides. So function and components of tissue engineering. So the functionality of what is the functionality or function requirement of any of tissue engineering is to restore, improve, and maintain the functionality of the host tissue. So if you are talking about the bone, so sole aim of tissue engineering is to restore, maintain, and improve its functionality. And the component of tissue engineering are basically cells, which is basically a unit part or basic part of any organ. A biomaterial, which we are using for the as a substitute for support or giving the extracellular matrix. Angiogenesis means basically the new blood formation. Our organ is not alive unless and until we are not having any kind of blood supply. So it is angiogenesis. So if you get stuck your hand or finger somewhere, you will find there is necrosis formations. So if as soon as body will never start formation of new blood cell, there may be chances that we need to cut that part. Okay, so angiogenesis is one of the important parameter, and growth factor and drugs are another factor. So these are basically the four factor which is a component of the tissue engineering. These are quoted with from my article itself. You just go through it and you will find the more details about that in there. Now, now if we understand what is tissue engineering and all, so what is the alternative of that, or what is the bone grafting we are using? We are just talking about the bone. So what is the bone grafting medium? So there are basically natural grafting and synthetic grafting. So in natural grafting, it is called as the autografting. So autografting means taking the bone or part from the some part of body to some part of non-infected part of the body and putting that in the infected part is called as the autograft. Isograft is basically the grafting in between the two similar identical. So if you are lucky enough that you are born with your twin brother and sister and they are ready to donate their organ or part, then it is called as the isograft. But how many of us has the twins is a question. So that's why the availability of isograft is not there. Then another grafting is called as the allografting. So allografting is basically transformation between the individual of the same species. So it is between the human to human. It is called as the allografting. And another grafting is called as the xenografting. So xenografting is transformation of organ between the in the different species is called as the xenografting. Now this entire grafting medium has some kind of disadvantage or cons associated with this. Now in case of autografting, suppose you are having your hand injured and you are replacing it with your some kind of leg bone. So you are creating the second doing a second surgery or second side morbidity. Why it is so? You are already having some problem with your hand, and you for doing it well, you are removing some part of from your leg bone. So you are also creating the second surgery and second side morbidity. So So this is again a problem associated with the autografting. Isografting availability is always a question. Allografting, there may be chances when we are doing the allografting, the transmission of disease can be there. So it is one of the difficulty. And xenografting, the rejection of graft is one of the major here, because body is built for the same species. Allograft may provide a solution, but when we are protein from some kind of xenograft like monkey or pig or someone, so body will start refusing that. So this is one of the challenge, and the solution for them is to replace this entire thing with the allograft. So allografting, alloplastic graft. Alloplastic graft is a synthetic material which is chemically synthesis as per the requirement of the host tissues. So when we are thinking for this alloplastic material, there are only four class of material which is available. Three class of material available. This is again quoted from my article and taken from some reference article again. So there are three class of material, either polymer, metal, or ceramic material. So only this class of material are available in any kind of grafting. So if you see at the middle, the green color is a natural material. So if we are talking about the bone, if you are able to see the cortical bone over there, so you will find, just a minute, I will try to check if I'm able to show it with the pointer. Okay, so if you see this cortical bone over here, okay, so what is the Young's fracture toughness in x-axis and Young's modulus? You just see, if you find out the Young's modulus, it is approximately 15 or 16 gigapascals. Now, how we can replace this cortical bone with the metallic implant, which we already showed in the reconstruction phase. Now, in reconstruction, what we are putting? We are putting the SS, stainless steel, or we are putting with the titanium 6Al 4 vanadium. This one, we are putting these two material. Now, what is the Young's modulus and fracture toughness? Which fracture toughness is much more higher than the required in x-axis. You can see, and in y-axis, you can see the fracture toughness of this titanium is approximately 107, and for stainless steel it is approximately 125 gigapascal and all. So you can assume what is the difference between the material available in when we are going with the reconstructions. Similarly, when we are going with the ceramic material, yes, it has some kind nearer to the value of this cortical bone. So mostly we are using the calcium phosphate bioceramic, which has the fracture toughness and Young's modulus, which is near to the this bone. And when we are going with the polymer, which is in this side, so if you see the polymer, you will come to know about it has the value or required property much lesser than the required one. So that's why we are using in bone tissue, we are using ceramic material, as explained in previous graph. Now, how we are using it? We are creating the scaffold. Now, what is the scaffold? Scaffold are temporary structure, physical structure that are used to replicate the in vivo values to allow the cell to influence the microenvironment. So just forget about this entire line. Just remember the scaffold is a structure which will give support to or channelize the growth of the cell. So scaffold as shown in this figure can be printed in thin fashion, can be printed in this fashion, can be printed in this fashion, and the cells can be grown in these holes. So it will basically channelize the growth of the cell, and it will give the support to the system. Now, what is the requirement of these biomaterials? When we are talking about, then it is the biocompatibility. It should be compatible with the host tissue. It should have the biodegradability, because we are moving from the reconstruction to the regeneration. So we want it to get regenerate. So it has the biodegradability. Scaffold architecture is one of the parameter. Osteoconductivity is one of the parameter. Now, what is meant by osteoconductivity? It seems to be difficult, but it is very easy. In medical science, osteo means bone. So bone conductivity should be there. So mechanical property should be there. Manufacturing technology and commercialization part should be there. So these are basically requirement for the bone tissue engineering. Uh, Now we are moving for the scaffold fabrications technique. So there are some conventional and non-conventional scaffold fabrication technique. In conventional fabrication, you will find gas forming, freeze drying, electro spinning, sol gel technique. So these are basically the conventional technique. If you understand what is meant by the scaffold, as shown over here, it is basically a 3D structure which has some kind of pores inside, where the cell can grow. Now, how we can get this kind of pores where the cell can grow from inside? So we are just understanding the technique associated with it. Now, everyone has from us had eaten this dokla. Okay, so in dokla there is some kind of pores inside. So that process of preparing a dokla is called as the gas forming. So gas will get entrapped in that, and after with that, it will come outside, making it more spongy in nature and creating the pores inside. So this is a simple technique which is called as the gas forming. Now, what is freeze drying? If you are making a dhokla or something and you are freezing it, and then we are allowing it to the moisture inside the dhokla or the component, which will get solidify, and just we are then heating it, it will get melted, creating the pore inside. Is called as the freeze drying. In solvent casting, what we are using, we are not using any kind of gas. We are putting some kind of material like a microsphere of sugar in that material, and then we allow it to dissolve in the water. So after once the microsphere of that sugar will get dissolved in the water, we will get the pores. So these are the conventional technique. And what are the non-conventional technique? So non-conventional technique are basically the 3D printing process. Now, what is the problem associated with this conventional technique? If you see the dhokla, just imagine the dhokla in front of you, and you will come to know about the pore size and pore interconnectivity is always a question. No one will assure that how the pores will get interconnected. Now we already play a game where we are showing how the cat will reach to the milk pot. Okay, so when we are very small kids, we are playing that game. If we are not having the interconnectivity, how the cell can be moved from one part to another part? It is not possible. That's why in any kind of scaffolding technique, it is required that it should be interconnected with each other. And the conventional technique does not give the assurity of that. And that's why the 3D printing is coming as the more promising field where we have the control architecture, control porosity, pore dimensions, and 100% interconnectivity can be obtained. So these are some different kind of technique which we already discussed. Now one more part which I explored during my research work is about the drug delivery rather than only concentrating on the organ regeneration, how it is possible to get the drug to be delivered with along with the bone regeneration. So when we are discussing again for the drug delivery, there are three routes. One is the parental drug delivery, which we are taking either with IV or through mouth, which required higher concentration, and drug delivery will be given for the extended period and have the adverse effect. Now you can everyone from us are survived from the COVID-19. Everyone has taken the Dolo 650. Okay, but it might be possible that for my anatomy, I may require to Dolo 250. For some people, so it may require 260. From some people to 65. But as a parental drug delivery, what we are supposed to give, everyone we are supposed to give the Dolo 650, which is a higher concentration of drug. And again, for the extended period, it might be possible that my fever get over in 1.5 days, but I have to complete the entire 5-day course and all, and it may have some kind of adverse effect. Then we have the local drug delivery, target-based drug delivery. Now, what we are doing in target-based drug delivery, it basically has the high cost. So it is come along with the nanoparticle coated with some kind of drug which are traveled towards the targeted tissue. For example, if there is injury in your leg, we are just taking intravenously some kind of nanoparticle. We are traveling that nanoparticle to that our leg part, and then the drug will get delivered. So high cost is also associated with the target-based drug delivery, and reduced ability to access doses. Dose cannot be as adjacent in that conditions. And the best route is the local drug delivery, which is the cost-effective. Which means if you are having pain in your leg, then you can apply some kind of cream or balm in that area itself. Why to apply the cream in entire body? So it is called as the local drug delivery, which is very cost-effective and easy to accumulate as per clinical need. So drug delivery can be done in two ways, either a diffusion where biomaterial is loaded with the biomaterial drug molecule and it will be diffused, or diffusion with the degradations. So if you are using I already talked about previous slide that the biomaterial should be a biodegradable one. So along with the diffusion, if the material is degradable, then it will start degrading and we will get the drug delivery. So accordingly, the research gap which I found out that it is very challenging to balance between the strength and porosity of 3D printed part, and 3D printing can be give the advantages for that. Ceramic scaffold is mostly considered only for the regeneration, but I try to explore how ceramic scaffold can be used for the regeneration and the drug delivery. Use of polymeric biomaterial as a drug vehicle is very known, but while the use of ceramic material in this field is very less. and very few article has been found for promoting the multifunctionality of ceramic scaffold by utilizing two and more functions. So these are basically research gap which I identified, and accordingly I framed my objective. Just keeping that part, and I'm directly taking you to the 3D printing of ceramic biomaterial and drug encapsulations. How I use 3D printing for ceramic 3D printing for ceramic printing, and how I encapsulated the drug for the application. So if you understand this diagram, you will completely understand the cycle of the tissue engineering. So for any kind of work, we require the CT scan. Then we need to, this green line is basically a engineering prospect, and this red line is basically the biological prospect, if you see. So we require a CT scan of the patient where we can do a CAD conversion. Once we are converting the CAD data, so once we are converting this into CAD, we are converting CAD data, then we are using the 3D bioplotter, which I used in VNIT, this one. And we are printing a 3D printed scaffold where we are encapsulating the drug as shown in this part. And similarly, we require to do a bone marrow aspiration. So from spongy bone, we can get the bone marrow, and then we can isolate the required cell line. And we can keep the cell line stored in this stem cell banking, and we can incubate it, and can see the morphology through inverted microscope and bring it to the biosafety cabinet. Now this drug impregnated scaffold are seeded with the required quantity of cell line, which is went to the in vitro testing, in vivo testing, followed by the animal trial and the human trials, and we will get the healthy individual. So this is basically things for a cycle for the tuning for the bone requirement, natural bone requirement. Now, 3D printing of ceramic work, the data which I am showing you is my PhD data which I worked on. So I use 4 different cases where I use beta TCP, that is beta form of tricalcium phosphate, hydroxyapatite, H means hydroxyapatite. The combination is in ratio of 80-20. Then I use beta TCP and aluminum oxides in 90-10, beta TCP and magnesium oxide in 90-10, and beta TCP and zirconia oxide in 90-10 ratios. So this diagram is I already shared in first slide, where we are using the CT scan, converting the CAD into CAD model, then we are doing the STL formations, then we are slicing it, then we are giving to the 3D printing process, and followed by the post processing. Now there is a slight difference between this cycle and bioprinting cycle. So when we are talking about the bioprinting, or especially the extrusion based bioprinting, the small difference in the fabrication process is that we need to prepare a identify the ceramic composite. Now the table which is mentioned over here is a ceramic composite which we are using. Then we need to use some kind of binder. Binder role is basically to bind this particle. As we are using this ceramic material, it does not have any kind of capacity to bind. For example, the toothpaste. If we remove the moisture from the toothpaste, whether we will get it in the form of paste, it is not possible. So we need to use the binder. Mostly we are using water in our household applications, but in case of tissue engineering, we require the polymer binder, which has capacity to hold the matrix. Then progen. Progens basically is a material which causes the porosity. So we need to prepare a slurry as shown here, and then this slurry is given to the low temperature printed of 3D bioplatter, which I used in my PhD, and currently also I am having a bioplot in our lab. Then we produce the porous scaffold, which is followed by the post processing, that is a sintering process, followed by the mechanical and biological testing. And once we are doing the sintering, we will do the drug impregnation, and then it will be bring to the in vitro testing. So this is the cycle of 3D printing in case of extruding based bioprinting process. Now 3D printing process, as previously discussed, it can require a ceramic composite, it required a slurry, and it required a binder. So binder which I use is 7.5% weight percent of the things, and then I use the bioprinter in which we have printed such kind of scaffolds. So this is a This is the example of heart wall. How this bioprinter, the same bioprinter machine I use for my. Now the parameter which I decided for different case study is mentioned over here. The printing parameter, dispensing pressure, temperature, hold between each layer, pre-flow, post-flow. So this might be too technical for you, but I'm just mentioning. So if anyone from you is interested, you can just contact. I will give the more detail of that. The article is already published. Again, you can check that. Now this is a post-processing part. How I did the post-processing. So I used to calculate the theoretical porosity. So theoretical porosity is calculated by this formula where I get the theoretical porosity with this D1, D2 and D3 is 50%. And I just check with the theoretical porosity along with the strength by using the some small apparatus, mechanical testing. This is the morpho SEM images of the 3D printed scaffold fold which I printed by using the bioplotter and all. So you will find it does not consist of only the macro pores. So if you consider this, this is basically a macro pores, but this also consists of the micro pores. So if you look at this, it consists of the micro pores also. So in any kind of scaffold printing, we required a micro pores and macro pores because the micro pores is responsible for the adherent of the cell line while the macro pores is responsible for the transition of the cells and transport of the required carbohydrate and the things which is required for the angiogenesis and other part. So both the porosity macro and micro pores is required in case of the scaffold. This is the XRD data of my all the three cases. So if you see draw powder and the powder centered after till 100, it has the same values. This is the FTIR data which shows that even after the post processing, we are not getting any new kind of bond formation, which means the material which is before the printing and after the printing and post processing are the same. So it is safer to use. This is the protocol which I use for the entity assay. Entity assay is basically the cell cytotoxicity. So the material which I use, whether it is toxic to the cells or not, we need to identify that before proposing it for the in vitro or in vivo and critical conditions. So I use this protocol where I use NG63 cell line, which is osteosarcoma cell line, to identify whether the material is toxic or not. So if you see, there is one control and there is one experimental material and how it is compatible. So if the reading is more than the 70%, which is already in this case, it is more than the 70% of what we are getting. So in that conditions, it is called as a material is a non-toxic. If the reading is less than the 70%, for example, if in control I am getting 100 cells and if in experimental I am getting only 50 cells, which means in 24 and 48 hours, so it means the material is toxic and it cannot be used to, it is basically toxic means it is killing the cells and it cannot be responsible for the regenerations. So these are the 4 cases MTTSA. And as I already talked about the degradation, the material which we are using, it should be degradable in nature. So this is the protocol for the degradation study. So if you see in 0 day, what is the weight of that material? It consists of different material which is mentioned over here. So in case of the zirconia and beta TCP, this is the something weight at 0 day. And after the 21 days, what is the weight? So you can find out that I am getting the good degradation in case of the this magnesium oxide where it has a good degradation after 21 days, followed by Al2O3, then followed by Ha, and then zirconia. Now the basically reasons is why the trend of this degradation is like this. So the reason basically magnesium oxide itself is a degradable in nature and beta TCP is also degradable in nature. That's why we are getting the higher degradation over here, while the other material are non-degradable in nature. So I already told you about after the sinting, I just impregnated a known amount of drug in that. This is the protocol for drug release profile. So in the first 0 day, I have some known quantity of drug over here, and I just evaluated it for the 30 days of study and identifying what is the drug release rate. So from this study, I concluded that higher porosity and compressive strength can be obtained in case 4, where we are using zirconia 10%. In case 2, we get the reveal the good strength along with the adequate porosity, but slow degradation, slow drug release, liberations, and biounit nature make it substandard in case of the tissue engineering. The compressive strength of 20% HN beta TCP and 10% magnesium oxide beta TCP are mentioned over here, 41 and 51 megapascal respectively, and they have shown the very good characteristic during the drug release. And that's why these two component or these two part are taken forward for the animal trial and preclinical studies. So the what is the future scope? So I already did a preclinical, in vitro testing. So the this one preclinical study and clinical study can be found, can be studied with this. Uh, if you are from a mechanical background, you can understand the shrinkage importance of shrinkage. So once we are printing the material, we are doing the post processing, that is sintering. It definitely cause some kind of shrinkage. So I have not considered any kind of shrinkage, but shrinkage allowances which we are considering in case of casting, and which is very well available in literature and database, is not available with the some kind of 3D printing. So getting the shrinkages allowances and considering it in 3D printing is one of the area which required to be worked on. And printing the complex architecture is another area. I use only one drug with for this 3D printed scaffold, while the multiple drug loading is one of the fascinating and futuristic area of research, which everyone can think on. Now I already talked about. I will give some future prospect where where anyone can think to work upon. And similarly, there are some challenges associated with the bioprinting. I'm going to explain about. So there are basically 8 challenges which are associated with the bioprinting. First challenge with the bioprinting is the poor shift fidelity. So now what we are doing in the with this bioprinting, we are printing the material one layer over the another layer. Now once we are increasing this layer by layer fashions, you can find out the dimensions of this older layer get deformed. So dimension of this top layer and the dimension of this bottom layer is something different, which is called as the poor shape fidelity. So this layer is not able to maintain their shape. Just okay. Second is about the triggering for extreme cell line. So seeding cell after printing. So there are some conditions where we can put the cell loaded scaffold or cell loaded bio ink. But in my case, I just printed the ceramic and then sintered it and then seeded the cell. So triggering mechanism for that is very difficult to understand. Non-uniform distribution, when we are seeding the cell line after the printing, non-uniform distribution of cell is one of the major challenge in case of the bio printing. And comprises with the cell viability. If you are doing the live cell printing, so the pneumatic pressure which caused during the bioprinting process is always compromised with the cell viability. It might be difficult for you to understand this, so you please feel free to ask after during the Q&A session. So poor and is resonance and accuracy, one of the challenge in case of the bioprinting. Scalability is major challenge in any kind of 3D printing, not only in the bioprinting. Definitely in bioprinting, it is predominantly considered as more, but 3D printing scalability is one of the major challenge, because the scaffold, if I'm printing only 1 or 2 pieces, then that is okay. What if required 500 kind of plates per day? How we can do that with the current bioprinting technique is one of the challenge. And controlled dissolution of scaffold in the body is one of the challenges. So dissolution basically means the degradation. So imagine if you are putting some kind of implant inside the body, how you can assure that it will have the controlled degradation from volumetric degradation in all side of the part. It is not going to happen. No, it is natural tendency, but it is a challenge that how we can assure that we will get the volumetric degradation of the printed scaffold. So this is one of the challenge where people need to work upon. And the next challenge is about the presence of growth factor in a body with cancer history. So if you are using, this is the example of the breast cancer, where both the breast are has removed, and if you are putting any kind of artificial implant or in this kind of cases, so there may be chances of getting again cancer, because there is already the growth factor, the required for the cancer cell formation is already inside the body. So how we can resolve this issue is one of the challenge. So this is about the application of 3D printing in tissue engineering and all. The lastly, I will just mention the one quote from Neil Armstrong, that research is about creating the new knowledge, but not only for knowledge for you or your city or your your environment, but it is for the mankind. So this the field of tissue engineering is really new, coming in very new field, very new research area. It has many research gaps over here, and the more people are required to work on this. No doubt it is something very difficult to understand, but yes, with over the time you can understand to try to research for creating the new knowledge. Thank you. I will open the forum for the question and answer.
Thank you, Dr. Ashutosh Bagde, sir, for such an insightful and thought-provoking session. Your discussion on the integration of tissue engineering with 3D printing has truly broadened our understanding of the potential and possibilities in this field. The examples and application you shared with us are not only fascinating, but also inspiring for future research and innovation.
Thank you.
Now we open our floor for the question and answer. If any participant have any type of the query or thought regarding the session, feel free to ask by raising your hand or dropping your queries into the chat box.
Thank you, Dr. Kavli.
Yeah,
So if
you can also see the comments.
Yeah. So if there are some questions, please feel free to ask. It might be very difficult for you to understand the tissue engineering. It is also difficult for me when I started working on that. But yes, what is the key difference? I have some question from Muthu Kumar sir. What is the key difference between the tissue engineering and implantation in terms of repairing and replacing the damaged tissue? So when we are talking about the implantation, it is basically the reconstruction. We are not regenerating. When we are putting any kind of implant inside a body, it is expected that it should be there for the longer duration, 10, 15, 20 years or throughout the life. So it is not going to regenerate the host tissue, while the main aim of our tissue engineering is to regenerate the entire tissues. Nilesh, can you stop this my sharing? I am unable to do that screen sharing. So next question is about.
Yeah, you can stop your screen sharing. No,
No, I am unable to get that. Here it is.
Sir, from my side, there is no problem.
Okay, no issue. I will check.
Just click on the participant. You see all the participant and their charts.
Sure. So next question is from Anil sir. Looking into various challenges, is there any scope of opening new domain of research? So the main challenge, there are many challenges in tissue engineering. I just highlighted the 8 part. So if you just take one challenge and start working, it is itself is a big domain to work on. Yeah.
so means I have personally visited your center and you are doing a lot and you're practicing this thing with the medical practitioner.
Yes.
Obviously, it's a very good kind of a combination of blend wherein one mechanical engineer with the biomedical skill and the doctors are working together. So, what did you think as far as your research is concerned? Ki, where you reach and what are the things which are to be covered? As
There are
I think you told me at that time also that about the tissue which you are going to develop and it would be a very good, great innovation or, so what exactly the status right now in your lab?
So I yesterday showed some kind of example of some case study where I did a clinical translation itself. So there are some cases where we actually did patients, we proved that how it is useful. But in case of the tissue engineering, it is very difficult to do any kind of clinical study. Even in developed country, in European countries also, they are not doing it. It is expected that after 2035, the technology is that much developed that we can do any kind of clinical validations. Till the in preclinical study, rabbit and rat model, I am regularly used to do such kind of cases. So tomorrow also I have planned some 8 cases for some kind of tissue engineering applications. So till animal study, yes, we are doing, but for human, there are many factors when regulatory approval and many things are there which is not in our control. So we are still struggling with that.
So
Yes, sir.
obviously, and that can be patented.
So people are patenting. I have not rushed towards the patenting of tissue engineering and all, but because it is a methodology, I am not basically interested for patenting such combinations and such methodology. But yes, people are doing such kind of things, and it is patentable. If you are
No, no.
doing some novel
Why
combination,
I am
it's
asking,
fine.
because it would be a very great invention in terms of, you know, the things, obviously, and if it would be patented or like that,
Yeah, yeah,
definitely, as
surely.
you are working
Yes,
in the big institution and the biomedical one,
yes,
so it would be a great achievement for India also, that
yes,
you are
yes,
generating the tissue and it would be a replacement,
yes.
you know,
So right now, so
not
we are working
replacement,
on two.
it's a regeneration.
Yes. So the study which I show is only for the bone. Right now we are working on regeneration of bone and cartilage both. We are working of chondromyocytes regeneration or cardiac tissue regeneration. So we are working on such cases also. Neural regeneration also we are working. So we have one question from Muthu Kumar sir, through some input into on coating on tissue and implantations. So both are the different fields, coating of tissue and implantation. Yes, tissue in tissue engineering we are coating the scaffold, but mostly it is with the collagen or polymer matrix, which is responsible for osteoconduction or osteointegration. But no, in case of implantation, we are coating mostly with the ceramic material only to get it osteointegrated completely with the host tissue. So it is completely a different field and it requires separate discussion. Omera Banu ma'am, please share your PPT. I will share some PPTs as requirement as required by mandated by the AICTE. Definitely, I will share that. Yes, sir. Thank you very much. I hope that you can understand everything. At least a 10% that is more beneficial for me because in our central India, very few people and groups are there only who are working in this. Manjit Kashpi, what should a hardcore mechanical do do to get into the biomedical field of research? Sir, I am a hardcore mechanical. I did my
Mhm.
diploma. I have not did 11th, 12th. I am not until I entered into the field of tissue engineering. I does not understand what is the cell and how it works then I eventually started working in cell culture and all. So if the person like me who does not understand the ABCD of biology, if he is working, definitely people will work on this part. So only
Sir,
thing is required a passion to follow it.
sir, one question again from my side.
Yes, sir. Yes, sir.
Sir, you in just last earlier slide, you have shown that two paths. One path was the by using the biomedical, you know, biological application. You know, there was the arrow and all, and there was one green kind of arrows wherein it was through your method, right?
Yes, sir.
You got my question?
Yes, I
That
got my point. That is the cycle
two
of
ways, you know,
transformation.
right? Which the
Yes,
diagram starts from the CT scan and then the CAD
yes,
modeling and then the you know that the machine in your VNIT and then last one. And
yes,
there was one biological methods which.
yes, sir.
So what what whether which is more useful, whether is it a time saving or if
No,
you
no,
compare the both the methods,
no, sir. It is
is
not
there any
about
advantage
comparing.
in your method?
No, no, sir, it is not about comparing. That diagram is basically the uh, collaborating diagram. So it is not about comparing. It basically has two parts. One is about the engineering, one is about the biological, and that
Yes.
needs to be integrated together at some point of time. So I'm just sharing the phase, but it is not comparing with the engineering and biological because only engineering cannot sustain in the tissue engineering kind of thing, and biology work cannot be sustained over there. So it is about complementing each other, not about the comparing.
Mhm.
Muthukuma sir, I already shared my phone number. Pavade sir, thank you very much. Pratik Joshi sir, thank you very much, sir. There are many more things that we are doing in tissue engineering. If you people get a time, just visit to our center.
Can you please elaborate that the bone marrow portion which you shown in that slide? Okay, taking the bone marrow and inserting it into that the object made by the 3D printer. So
Yeah.
yeah, this one. Yeah, 21 numbers.
So we are showing bone marrow. This area basically because we required the cell. Now there are two kinds of cell responsible for the regeneration. One is about the osteocyte and one is about the osteoblast and osteoclast. So osteoblast cell line are basically the cell line which is responsible for the bone formation, and osteoclast cell line is the cell line which is responsible for the bone deformation. So bone itself has a natural tendency of the regeneration. Okay. So there are two kinds of cell line. So how we can get the cell line? We can get it from the bone marrow, because bone marrow consists of the stem cell basically. Stem cell is our basic cells from which we all are created. Okay. So from bone marrow we are getting the cells. So there are some process. I am just showing the 2-3 parts. This 1, 2, 3, 4. But there are complete process and protocol. So from bone marrow we are just centrifuging and obtaining differentiating the different kind of stem cells. We are storing that cell in the ultra low freezer for the longer duration. Then we are incubating that cell in CO2 incubator to get the sufficient strength, sufficient quantity or number of cells. Then we will see the morphology, the count of cell available over here. It is very small process I am showing, but it is a lengthy one itself. Then whatever the cell we are isolated, we are printing and seeding this cell with the engineering line and the biological line together in the biosafety cabinet, for which we are doing the testing, in vitro testing, in lab condition, in vivo conditions, and then we will go with the surgical condition, surgery.
Okay.
So this is basically, I'm just trying to explain very short, but it's not that short.
Yeah, yeah, obviously. What would be the case in case of this anatomical surgeries, wherein in case of any accidents or like that, wherein the portion of that skull, yesterday there was a session on that mimic and thematic, right? But how it would be helpful in that cases,
So
anatomical surgeries, like
in craniotomy, we does not look into the tissue engineering prospect, because
okay,
after 30 years, I study also I told about, after 30 years or 25 years, the cranial bone stopped regeneration. The reason, it does not have any kind of the angiogenesis, blood cells to be formed, blood vessels. So our skull does not have any kind of blood vessels. It is completely made of the cortical bone, not the cancellous bone. Okay. So that's why regeneration gets stopped after the some time. Okay. And once there is no blood vessel inside, so we cannot get the regeneration itself. So that's why in cranial portion, we are just looking for the reconstruction. So what we are doing reconstruction yesterday, I showed the 10 cases study which I did with ISC, that we are reconstructed the anatomy or the curvature by using the PMMA material, by using the 3D printing. So regeneration is not possible with the cranial part.
cranial.
Yeah. So we have question from the Ankit. Can we use the scaffold for dental part? If yes, what are the material for it? So what basically a dental part you want to regenerate? It basically depend on that. Tooth cannot be get regenerated, because tooth consists of different kind of layer, dentine, pulpate, and many parts over there. So it cannot get regenerated. But if yes, it is about the bone associated near to the root of the tooth, yes, it is possible. And in that condition, we need to use ceramic material, polymer material. It is as per the requirement what we are thinking for. So we cannot give a single line answer for such kind of thing, because we need to understand the application. AVN, Dr. Shubhangi, AVN is also prepared with tissue. AVN, I'm not understanding. Can you elaborate what is AVN? Ganesh sir, thank you very much. Shubhangi ma'am, if you can write what is AVN, then I may be in position to answer. We need to use case study journal for citation purpose, sir. You just go with the Google Scholar. You will find more than 30 articles which are published, and there are many more upcoming soon. So you just go with Google Scholar. Dr. Suresh Purmare, thank you very much, sir. So necrosis cases, Shubhangi ma'am, yes, it can be, but we need to see where it has some kind of angiogenesis. Regeneration, the basic requirement, if you see that diagram or triangle which I have shown, the component of tissue engineering, angiogenesis is one of the parameter. So necrosis basically formed because there is the obstruction or distractions in that angiogenesis process. So it is very difficult in that condition, but if there is some chances of that, then we can do it. So in that condition, what we need to think about, what we are working on. So we are working on cardiovascular, like veins and arteries regeneration part. So if there is
Right.
some kind of necrosis, is it possible for us to regenerate the arteries and veins? So we are working on that also. So
That too,
thank you very much.
I think mostly concerned with the hard tissue, soft tissues, like
Yes,
not concerned with the mostly with the bones and all. It's
yes,
concerned with the arteries, veins, and
yes,
the soft kind of bones. Very
yes. Jitendra sir, thank you very much. So if there are some more questions.
one again small question.
Yes, sir, please, please. I'm ready.
Yeah.
Yeah.
Yes, yeah. As means in mimics, right? In mimics, by using segmentation, we can concentrate on the soft tissues, right? Would it would be helpful for that? Because as we come to know that in tissue engineering, there must be some kind of the blood vessels and all. So the segmentation, we know that in mimic segmentation is a tool wherein in which kind of the bone, according to the bone densities or the segmentation, we can see that parts,
Mm.
right? So my question is that through using mimics, we can focus on the segmentation method, and wherein can we, whether it would be useful for us to focus on the soft tissues.
So,
My
sir,
question.
Mimic is basically a simple tool which can convert the CT scan data into a CAD model. It does not
Huh.
help us any kind of regeneration. It is only a
No,
CAD
no, not
model. Okay.
regeneration. I'm
Yeah,
not
yeah.
talking
So,
about
yes, so it
regeneration.
is useful. Like, it is useful. If there is some kind of soft tissues is get damaged and you want to print
Yes,
a custom patient specific soft tissue, then it is useful. Definitely,
like
it is useful.
from MRI data, like
Yes,
those
yes, it
one.
is useful.
Yes.
If you are going for the PSI, then it is definitely useful.
Okay. Okay.
Dr. Umera, how much is the cost for to regenerate the arteries? Ma'am, we cannot say the cost because this field is still in a infancy and in research condition. So we cannot say any cost.
Ashutosh,
Sir.
yeah, I want to know which applications are being successfully completed using this tissue engineering and organ regeneration, which has been implanted also in the body, and you are getting the results.
So, sir, yesterday I showed one case of 3D printed. If you remember, but there is one lady's case where we just resected the tumor from the mandible, and then we used the customized surgical tool which is developed by Dr. Sandeep, and then we put it a 3D printed ceramic graft. So we got a good result with that graft. We followed the patient with last 3-4 years, and uh, now she is getting older, so she has some different pains, but that is not associated with the implant which we did. She has some different conditions due to which she is now taking rest and all. But implant which we have built, so we got a good result. When we are doing this droplet test, we found some kind of angiogenesis over there. So which means bone is getting regenerated because angiogenesis bone formation is blood cells formation is there. So yes, this is one case that we work exactly. But if you are looking from
Okay.
research perspective, there are many. So liver regeneration is one of the easy. Skin regeneration is one of the easiest part. So people to be okay because it is not intraocular. It is only the surface part. So skin regeneration is the one of the easiest part to get regenerate.
Okay, right. And are there any doctoral studies are going on in Varda on this tissue engineering?
So we are doing many. We are not doing with any kind of clinical because there are regulatory conditions which not yet cleared with the tissue engineering. So we don't want to treat the patient as a guinea pig. So what we are doing with the animal trials and in vitro conditions, there are many cases.
Okay, but in India people are not trying anything
So
with the human.
So it is very difficult to go with the human. The first thing is about the regulatory approval. So there is no clear-cut pathway available for the regulatory approval. What is required for the regulatory approval is required for this tissue engineering. So it is not clear. That's why people are not going. And second thing is about the technology development. So still the technology for this tissue engineering is not fully developed.
Okay. Do you know any foreign universities wherein this tissue engineering they are being successfully they are taking the cases of the humans and there they have done some
No.
successful case studies?
No, sir. One or
No.
two cases might
So
be there, like the case we did in DMIHR for one case. One or two cases with the bone is there. Skin, there are many
okay.
because for such
Uh,
what is meant by the skin regeneration, sir? If there is some kind of wound, diabetic wound or some kind of
uh,
injury, and there is some wound, it should get
uh,
regenerated. If say there is
right.
some burning of
Uh,
hand, so it should get regenerated.
uh,
So for skin,
right.
there are n number of things available, but for the internal
Already, yes.
organ, it is not there. And it is
Right.
expected that 2035, developing country will also move towards the clinical trial of this. But for uh, preclinical study, yes, there are many.
Okay. Okay. Good. So thank you
Okay,
so
I
much.
think
If
Thank
there
you.
are no queries from the participants, one of these is how much is the cost to regenerate artery?
I answered that, so we cannot give
yes,
it more
Okay,
details.
he answered that all questions.
Yes, yes, yes. Okay, okay. So I think there are no questions now. Over to
Yes.
Nirvan sir.
Thank you all the participants for your excellent questions, and a big thank to Dr. Ashutosh Bagde for addressing them so comprehensively. This interaction discussion has added even more value to this incredible session. Now we wrap up technical session 7 on application of tissue engineering in 3D printing. On behalf of the organizing committee, I would like to express my heartfelt gratitude to Dr. Ashutosh Bagde for his invaluable contribution to this FDP program. Thank you, sir.
Thank you very much to Jaju sir, Abhay sir, and
Thank
Nilesh.
you.
See you
Thank you
soon.
so much. Yeah.
Yeah.
Thank you so much, Ashutosh, for sparing the time and sharing your research and giving the new directions to the participants because this tissue engineering and like similar to kind of discussions which you had yesterday also, like organ transplant and the success which you are getting into that. This will give the participants new direction of work because engineers they can do wonders if they join hands with the biomedical people,
Yes, sir.
right,
Yes.
and medical field people. So
Yes, sir.
thank you so much.
Thank you.
For the participants, there is instruction that you can just take the break of 15 minutes, and the next session shall be from 7:30 p.m. Thank you so much.
Thank you, sir. See you soon.
Thank you. See you. Yeah.
That second session is again very interesting.